Hello everyone, my name is Chinsung Park and I'm from the Georgia Tech, also SK Hynix. Today, I present our recent work. The title is Endurance Enhancement in Low Operating Voltage, the Scavenged SOI FEFETs. Here is the outline. I start from the background and motivation, and I move on the experiment details, and I show the result and discussion, and I conclude my talk. The first is a background and motivation. FEFET regarded as a future emerging non-volatile memory device, but it still has many challenges. Currently, in memory industry, there is an explosive demand for memory. The reason for this demands is that there is huge computing requirements and there is a boost from the ChatGPT 3.5, ChatGPT 4, and even for the ChatGPT 4.5, there is a more than 10,000 times requirement for the computing performance. So that requirements also boosts the memory demands. So currently, we are using SRAM, DRAM, and flash devices. But for future devices, this SRAM and DRAM is not sufficient because future device needs lower power. So in that perspective, the standby power, this FEFT can be a very good candidate because that standby power is much lower. And also, write energy and write time is not below the SRAM DRAM, but it is pretty comparable with the SRAM DRAM device. However, for the light voltage, it is lower than flash memory device, but still it is higher the write voltage required comparing to SRAM and DRAM. And also the endurance perspective is much lower endurance and it is still bad. So then we have the problems, the challenges for the FEFET. First is endurance and second is the write voltage. So to resolve the problems, our research community focused and we had a gateway engineering like adding some layers to improve the endurance or some treatment is like a nitrogen fluorine etc. But still we are looking for the better solution. And also to decrease the write voltage, we scaled the gate stack, the fidelity layer, also IL layer. So we call it IL scavenging, and I talk in detail in the later, and also I research this IL scavenging in this research. And also in this study, we also used SOI in FEFET. SOI, you already know silicon on insulator, and this silicon on insulator wafer is still itself has the benefit. The benefit is a leakage decrease. In this silicon SOI wafer has this the BUX, butyl oxide layer, and this BUX layer has the decreased the leakage from the source to drain and the source drain to the body. So if just use this SO vapor, we have leakage decrease, then it can increase the on current. So there is the huge benefit with this SOI. So the logic industry, they started to use this SOI wafer. The Samsung and GlobalFoundries, they use 18 nanometer and 22 nanometer, they use the SOI wafer before they started using the FinFET technology. But nowadays, there is a demand for the current boosting technique for the petty area for memory industries. So there is still demand for the interest in the SOI vapor. FEFET on SOI in the 2017 IDM, there is a 22 nanometer FD-SOI FEFT result is published. But still, there is no scavenging study on SOI FEFTs. That is a motivation of this study. FEFT concept is very simple. Depending on the position of oxygen atom in HGO, we currently using HGO in common in the as a ferrite layer, and this oxygen atom is about lower than polarization up, and oxygen atom in the top than polarization down. So depending on the oxygen atom position, we have different the heat stages, the polarization up and polarization down. So if we deposit this ferrite layer on the MOSFET structure, then if we measure the IDVG characteristics, then we have two different results. The first, if the polarization is lower, is the polarization down, then it called it low VT state. We have this the blue curve. And if the high VT state polarization up, then we have this graph. So there is a difference depending on this polarization state. We have a different the result. So if we measure at 0 voltage, then the current is completely different. What in low VT state is the current is high, and high VT state is the current low. So using this device, we can save the data because we have two different states. Next is experimental details. So in this research, we made 4 different devices. The reason for this, we want to do apple-to-apple comparison. The first category for the comparison is a silicon FEFET versus SOI FEFET. The second category is the non-scavenging device and the scavenging device. So we have 4 different devices, and we have 2 different categories, silicon versus SOI and non-scavenging versus the scavenging. And for the non-scavenging device versus the scavenging device, we have 2 different TIN thickness. TIN 2 nanometer device for the scavenging device, and TIN 12 nanometer device for the non-scavenging device. I explain in detail why we chose these 2 different thickness. And here is a process flow of SOI FEFT fabrication. So the key difference between this SOI FEFT fabrication versus normal silicon FET fabrication is the mesa patterning. The mesa patterning is an etching process, the silicon etching. So here is an SOI wafer. You can see this is a side view, and on the top there is a silicon epitaxial layer, and on the bottom there is silicon epitaxial bulk layer. And the mesa patterning, we only remained the silicon active area, and the other unused non-active area has been removed using the silicon etching. So you can see here only this yellow line, yellow dots represent this active area, and the other blue line represents the oxide layer. So because after silicon etching, the top unused silicon active area has been removed, so only the oxide layer has been shown here. This is the top view. And then we deposit 8 nanometer thermal hafnium zircon oxide, and then we deposit titanium deposition. Here we made different TIN thickness MOSFET devices, and we found that in 12 nanometer device, just a normal reference device, comparing this device, TIN 2 nanometer device has a higher polarization, 2-pair is much higher compared to 12 nanometer. And we had a TEM analysis, and we found that this 2 nanometer device, the IO layer is thinner. So, and then we call it just scavenged. The IO is a scavenged and scavenged device. So TI 2 nanometer is very effective in the scavenging the IO. So that's why we chose TI 2 nanometer is a scavenged and 12 nanometer TI is the non-scavenging device. And then we have annealing the fabricated layer 500C and the 32nd, and PTTI deposition as a gate metal layer, and ILD passivation and aluminum metallization. We did also the FPGA process. And here is the mechanism figure of the scavenging DIL. On top of the TIL layer, we deposit platinum and titanium, and titanium this material is a very reactive material. This titanium is form the titanium oxide with the oxygen atom. So, and this oxygen atom is coming from the silicon oxide IL layer and is diffused the HGO layer, and it form titanium oxide layer below tile layer. And if this titanium nitride layer is thicker, it's not easy to diffuse to the tile layer. So that's why the TIA 2 nanometer layer is very effective to scavenge the IL and to form the titanium oxide layer. And result in discussion. Before move to our recent work, I want to show our earlier work, the scavenging at Germany Moscow, because I want to explain a little bit how to measure the PB measurement to explain the scavenging device working. So here in this work, we made three different gate metal, and we applied the same voltage, minus 2 volt and 2 volt, and only this platinum titanium layer device only showed the switching. The other devices at 2 volt doesn't switch it. So reason for this platinum titanium metal layer is a very effective to reduce the scavenging. So that's why only this device shows the switching. So the same methodology we applied SOI FEFET, and we have two different devices. One is a non-scavenging device and the other one is scavenging device. So you can see here we apply the same 3 volt, minus 3 and the 3 volt, and only scavenging device has a nice PV and IV curve. There is a switching. So this non-scavenging device, the IL is still thick, but scavenging device is IV thinner. So you can see in the average VC measurement, the voltage drop is around 0.5 volt from non-scavenging device and scavenging device. Also, we want to compare with the silicon FEFET. You can see at 2 volt, the both non-scavenging and scavenging device doesn't switch in the silicon and SOI. But at 3 volt, likewise, the SOI result, the scavenging device switch it. So I summarize the trend is pretty similar in both silicon and SOI FET, and I summarize on the right figure. So from the non-scavenging device and the scavenging device, there is a voltage drop is around 0.5 volt, and that trend is pretty similar between the silicon and SOI FEFET. That is the first observation. And then we measured the memory window. So to get the memory window measurement, we measured the IDVG and using the DC scheme and also pulse IDVG scheme. And you can see, depending on the polarization, we had a low VT state and in high VT state we can see, so we can measure the memory window for both scavenged device and the non-scavenged device. Also, same thing happen in an SOI. The scavenged device is a memory window we can measure, and non-scavenged device also we can measure the memory window. And then I summarized the memory window versus the voltage. And first, silicon FEFET, you can see the memory window, the maximum memory window is pretty similar, around the 0.7 volt and 0.8 volt. However, there is a different thing. The scavenging device is the to get the maximum memory window in the scavenging device. The voltage required voltage is much lower than the non-scavenging device. It's only around 3 and 3.5 volt is necessary to get the memory window around 0.7. And the same trend happened in the SOI FET. SOI FET also has a maximum memory window around the 0.7 volt and is a much lower voltage required for the scavenging device. So same trend happened in both the silicon and SOI FET for memory window measurement. And we also measured the endurance. And this endurance perspective, silicon and SOI FEFT, there is a slightly different. The difference is, first, in the scavenging device, the perspective, there is a similar in between the silicon and SOI. There is a one or the higher endurance benefit if we using the scavenging technique. So in the SOI FET, the, the, the endurance is a 1E6 and the non-scavenging device is a 1E5. And the same thing happened in the silicon FET. However, there is a difference. In an SOI FEFET has a benefit. This wafer has a benefit comparing to silicon FEFET. You can see in silicon scavenged SOI FEFT has endurance 1E6, and the scavenging silicon FEFT has a 1E4. So two other higher endurance benefit if we used SOI FEFT. So for the scavenging, so the scavenging device has a one of the higher endurance benefit. That is pretty understandable because scavenging device has a thinner IL. Thinner IL represent is a less chance to get trapped inside the silicon oxide. So it's a thinner IL than can cause the better endurance. However, this SOI FET is a better endurance compared to silicon FET. There is still unclear why the endurance is better than the silicon FEFT. There is more research are required. And also, we measured lead after light delay. For both silicon FET and SOI FET, from 100 seconds to 1 microsecond, the memory window is pretty consistent. So even at the very fast 1 microseconds the lead delay, we can see the memory window for both silicon and SOI FEFETs. So conclusion. So in this study, we made 4 different devices. The non-scavenging device and scavenging device for both silicon and SOI FET. And we measure the Cauchy voltage. There is a drop from the non-scavenging device to scavenging device around 0.5 volt. But that trend is pretty consistent in the silicon FET and SOI FEFET. So second thing is the memory window measurement. We see that in both silicon and SOI FEFET, the maximum memory window is around 0.7 and 0.8 volt. That is almost similar. However, the scavenging device is a much lower voltage than the non-scavenging device. So that is also the similar trend in silicon and SOI FET. However, in perspective of endurance, the data is slightly different. The scavenging device has a benefit in endurance in the one or the higher in both silicon and SOI. However, this SOI wafer, SOI FET, is a better endurance than silicon, is around two order higher endurance. So that is there is a different, and SOI wafer is a better endurance. Thank you for your kind attention, and thank you very much.